So we have a new overflow room today. Nobody needs it. I think a couple people are over there. It's 240, which is one room in that direction. So the question somebody asked was, how do you ask questions if you're sitting in the other room? And the answer is that there's a website on the class webpage where you type in questions, and these folks in the front row will either answer them or ask me in the small chance that they can't answer them. Okay. So we're going to continue today with single processor machines, but let me not forget to say we also have the forms you have to fill out to get the supercomputer accounts at NERSC, where you're going to do your homework. And so hopefully I'll be reminded to end a few minutes early so you can fill out the forms and they can be collected and so forth. Got to sign them. So it turns out that I need to tell you a little bit about the details of the hardware in the first lecture or two. And the goal of that is to make sure that you understand where performance goes, but to give you enough of a mental model so that you can use it later, right? So we're not going to concentrate on the hardware levels throughout the course, but you have to know what's under there so you have the right mental model to do good programming later. And I'm going to start by telling you about single processor machines and do a case study of matrix multiply. And the motivation is even if you write a program on a single processor machine, the chances are it's going to run at less than 10% of the peak speed of the machine. So you already have a factor of 10 that goes away, that traditionally goes away on these machines. And when I say 10% of peak is the manufacturer's advertised top speed of the machine. Can't go any faster than that. And that's measuring floating point operations per second. So where does all that performance go? Where does that factor of 10 go? A lot of it is in the memory system. A lot of it is because your program, hidden to you, is spending all its time moving data back and forth between different slow layers of the memory up into the processor where it can actually do the work. And moving data takes much, much longer and actually takes much more energy than doing arithmetic and logic. So what I'm going to do is look under the hood in this lecture about how complicated this is and try to give you a simpler mental model of how to deal with it. So here are the conclusions that you could draw from today's lecture. And different people can draw different conclusions. You might say that computer architecture is really fascinating. I really like all this complexity. And I want to understand why the really, really simple programs that I'm going to show you give you answers that are so complex that depending on how you run them, they're just vastly different in speed, factors of 60. You may also conclude that, that's okay, but I'd really rather learn how to design an algorithm that will be fast no matter what architecture it runs on. I want to know just enough about those architectures so that I can write my program in an effective way, and the chances are good it'll run fast anywhere. You could also conclude is that most of the time I want somebody to handle all those details for me. I just want to know where to get the fastest software where somebody has hidden all that stuff in there so that I can just use it, and so I don't have to worry about it. And all of those are valid conclusions, depending on what you like to do. And in fact, in the course of this semester, in the course of your career, you may have all three different conclusions. You may decide you're interested in making one particular algorithm run really fast, but the other ones, you just want to grab the fastest ones that are available. That's somebody else's problem. So I'm going to do this deep dive for one lecture, or 1.5 lectures, and then we're going to move up the hierarchy and give you abstractions so that you can think at a high level of what your algorithm should look like so they'll probably run fast. Okay, so here's the outline of the course. I'm going to give you some idealized model of what a single processor does, and then I'll tell you what the actual costs are, what hardware kind of looks like. And that is going to have to do with the topic of memory hierarchies. The fact is that you have many, many different layers of memory, from small to large and from fast to slow. And they've all been put in there by manufacturers because that's the only way they can figure out to go reasonably fast. And then what I'm going to do is run an incredibly simple benchmark. A benchmark is a very simple program that just measures how fast the machine goes. And all it's going to do is load words from memory in order. And I'm going to measure how fast that goes. How complicated could such a program be? It's amazingly complicated in terms of its behavior. And I'll show you some interesting plots and show how those plots, we can sort of reverse engineer what the hardware has to look like. And then I'll talk about the fact that there's also parallelism within single processors that the hardware does for you automatically if you write your program the right way. And that's separate from the parallelism we'll be spending most of the semester on, which you have to do yourself explicitly across many, many processors. And then I'll take all those ideas and I'll apply them to optimizing matrix multiplication, which is part of your homework number 1. And I'm going to try to use performance models to understand its performance. And in the case of matrix multiply, which is probably the most studied algorithm ever, there are actually lower bounds on how much data has to move, no matter how you implement it, how much data has to move between fast memory and slow memory. And there are algorithms that attain these lower bounds. So I will go over that material. So let me give you a totally idealized model, and then tell you why it's, which you may have already in your mind, but then tell you why it's wrong. And let me say there are a few more seats. Good, okay. So your idealized processor model is that your processor has a bunch of addresses. That's how it names locations in memory. Variable A is stored at location 1, variable B is stored at location 2. And then what operations does it perform? It's going to say, please read location 1 into a register. Please read location 2 into a register, and then add them and put the answer in another register. And when you're done, write out the answer to location 3. So there's basically read into a register from memory, write the answer back from a register to memory, and then do some arithmetic on data in registers. So how does it decide what operations to do? Well, that's your program, right? You've written a program, and your program is executed in the order of the instructions that you wrote it. And then, and you write in a high-level language with instructions like A equals B plus C. And then what all the hardware does, it's kind of straightforward. It would take an instruction like A equals B plus C and translate it into the sequence of 4 low-level instructions. Get B out of memory, wherever it's stored at its address, and put that in register 1. Get C out of memory and put that in register 2. Do the arithmetic, put the answer in register 3, and then write it back. And it's just sort of a very simple translation that goes that way. And then your idealized cost is you just count how many of these low-level assembly language instructions you execute, and that tells you how fast things go. Well, that's not nearly good enough. So in the real world, processors not only have registers, which are connected to the adders and the multipliers, they have caches. They have not just the main memory, they have a little fast memory, which is close to the processor. So it's small. It can store values of the data you've just recently used, right? So the hardware guesses that once you've touched data, you're probably going to use it again, so it keeps it there. And so that may be a good guess or it may be a bad guess. And when you go get it, it's much cheaper to get it in your cache than in your faraway memory. And I think I gave this example last time. Imagine you're sitting at your desk and you're writing something and you need a pencil. And so the first thing you're going to do is look at the top of your desk and grab a pencil if it's there. That's the fastest thing you can do. That's a register. And if it's not there, you have to open a drawer, get out a box of pencils, put it up in your desk. That takes a little bit longer, and that would be the cache. And if it's not in the cache, you have to walk down the hall to the closet and get a big box of pencils, bring it back. That's the main memory. And so each of these layers is slower and larger than the previous one, and it's a natural kind of economic model that applies to computer hardware as well as it does to pencils. And you can have many, many layers, but there's at least going to be registers and caches and main memory. The other thing about real hardware is that it's parallel. The memory and the arithmetic can all happen at the same time, and the hardware will try to do that for you automatically. And the other thing is that you can have pipelines. So if you know how a factory works, a pipeline in a factory where you have a manufacturing line where different parts of the process are running at the same time, that's also something that the hardware can do if you set up things well. So in theory, the compilers and the hardware understand all of this perfectly well, and you could just write your nice simple program and it would take advantage of all these things. But in practice, they don't do a very good job. And in fact, just for homework 1, you'll explore that a little bit. You'll try different compilers and discover that the same program will run at very different speeds depending on which compiler you use, GCC versus ICC and other than that. And in particular, if it turns out that a completely different algorithm is the right one to use, like you may have wanted to reorganize matrix multiply in a completely different way, the chances are the compiler doesn't know enough math or computer science to completely change your algorithm. And so, in theory, there's no difference between theory and practice, but in practice there is. This probably goes back to Aristotle, but that's the oldest attribution I could find. So you do have to pay some attention to this stuff. Okay, so that's idealized versus actual costs. And now I'm going to tell you more about what these memory hierarchies look like. And so the reason people build caches is that most programs have what is called a locality. And that means that if you want to access a word in memory, an entry of a matrix, the chances are you want to access nearby words too, because that's the way most programs are written. You touch an entry of a column of a matrix, chances are you want to go down the column and get its neighbors. The hardware is going to take advantage of that for you. That's called spatial locality. Stuff that's close is likely to be accessed. The other thing is temporal locality. That means if you touch an entry and do some arithmetic on it, the chances are you're going to want to use it again in the near future. So it might as well keep it close to the hardware for you. And so the way hardware is organized to take advantage of those two common properties is in this memory hierarchy fashion. From the processor, and this is the closest, all the way out to disk and tape is the lowest level. So here is where your registers are. Here is where your part of the program as it executes the instructions, it interprets what an add means, interprets what a write means. And here is the on-chip cache. That's the fastest memory that I was telling you about. So if your data, if you need to put it in the register to do the arithmetic, you go to the on-chip cache. It's very close. It's only 1 nanosecond away. Since it's so close, it can't be very large, just physical limits. So maybe it's kilobytes in size. And then you get it really fast and you can do your arithmetic. And if it's not there, you might go to a second level cache, which might be a little bit farther away on the chip, or it might be entirely off chip, which makes it quite a bit slower. Sometimes that's called static RAM. And that is maybe 10 times slower, 10 nanoseconds, but it can be 1,000 times bigger. So we're talking megabytes there. If it's not in that level of cache, then you might go to main memory, which is DRAM, dynamic RAM. And there we're talking about another factor of 10 and how much it slows down, 100 nanoseconds. But it's another factor of 1,000 in size, so gigabytes on your laptop in your main memory. If it's not there, you may have to go to disk. And there, it's many orders of magnitude once you go to disk. We're talking 10 milliseconds to get data off there, but you can have terabytes. I don't know how big your disk is in your laptop. And then if you run a supercomputer center, there's a tape drive, right? There's this huge kind of robot which goes and grabs tapes off a shelf and puts them in a machine automatically for you. And that's going to take many, many seconds, if not a minute, for the robot to go get the tape. But you can have your petabyte data storage of climate data there. So this is what real machines look like. And let me also say that these numbers here, the speeds, they're not constant. They're also changing. They're getting better. But they're getting better at different rates. So last time I showed you this plot of Moore's law. So here's the vertical axis, which is speed on a log scale. So a straight line is the exponential growth. The horizontal axis is time. And this was the picture I told you that says because the transistors are getting smaller, if you look at what one chip can do, then it's getting better at 60% a year. Well, that's the chip. It turns out memory is also getting better. But if you ask how much faster is memory getting, how long does it take to go from all the way from here to there, from the chip to the DRAM, it's getting better only at 7% a year. So this gap is bad today, orders of magnitude, and it's growing exponentially over time. So that means it's only going to become more and more important to pay attention to this stuff as things move forward. So here are the approaches to handling that big gap, which is in memory latency. So the latency, just to repeat it, is you initiate a read instruction. Please go to DRAM and get me some data, and then bring it back. How long do you have to wait? And there's a question. Maybe you could pass David the microphone.
Why is it that the DRAM evolves more slowly than the processors?
So in part, that's because you have to push electrons. So the question is, why is the DRAM evolving more slowly? So that's a good electrical engineering question. Part of the answer is that the inherent cost involves building up enough charge on a wire that has to go all the way off of one chip onto another chip, and you just can't do that very fast. It requires a lot of power and time to move all those electrons over there, and that's not subject to Moore's law. So different physical laws are causing these things to happen. So here are some of the approaches to handling memory latency. One of them is and the main one is you just don't do those memory operations. You store everything in cache and reuse it. And so that's something where we want to take advantage of temporal locality. Once you get it, put it in cache, chances are you're going to use it again. The other thing we want to take advantage of is that there's two ways to measure how fast a memory is. One of them is latency, which I said is how long it takes to get the data. But the other one is bandwidth. I'll define that a little bit more carefully later, but that's a different physical property. And bandwidth is once the memory starts shipping you data, how fast can it pack data together? I mean, it sends you the first word, you got to wait a long time, but suppose you want a whole sequence of words that are all stored together. How fast can it do that? It can do that much more quickly. So let me give you a physical example of bandwidth versus latency. Let me talk about the freeway from Berkeley to Sacramento. The latency is how long it takes you to drive at 55 miles an hour if you don't break the law from Berkeley to Sacramento, right? It's the distance divided by 55 miles an hour. What's the bandwidth of the freeway? Well, that depends on how many lanes it has, how many cars, how close together the cars park. It's how many cars per minute can actually drive from Berkeley to Sacramento. That's a different number, right? It depends on the lanes, how close the cars are packed together. That's the bandwidth. And hardware has the same properties, right? So you can pack together a lot of bits, and they start arriving all in a big chunk, and that is the bandwidth, and that's also getting better over time. That's getting better at 23% here. Okay, so the latency is 7%, the bandwidth is 23%, and then the raw speed on the chip is 60%. So they're all growing apart, but we have this extra resource to take advantage of. And so how do we do that? We take advantage of spatial locality. When we go to DRAM and we get a word of memory, we take advantage of the fact that we probably just don't want that word, we want all its neighbors. We want to get the whole column of the matrix. And so we're going to fetch a whole bunch of words, and they're going to arrive much more quickly than getting them one at a time. So that's taking advantage of spatial locality. So there's also the possibility of parallelism. If you do want to fetch lots of different locations in memory at the same time, you can just pipe them into the memory system, and it'll try to run in parallel with the main processor. The other thing it can, so that's overlapping. Yeah, that's concurrency in the execution stream. So you can load the whole multiple arrays. And the other thing is that sometimes the computer tries to guess what you're going to need next. That's called prefetching. It says, you just got address 1, then you got address 2, then you got address 3. I'm going to guess you want address 4 next. I'm just going to go get it ahead of time. That's called prefetching. And in fact, modern hardware has machine learning algorithms in it that try to look at your instruction stream and build a model of it and guess what you're going to want next and go get it ahead of time. And so this is very hard to make a simple model of all that. But I'm going to run some benchmarks for you and show you what all that means. So here are the basic terms about how a cache works. So some of this is to repeat what I said before. It's this small, fast memory. And so I have to figure out how's it going to work. So suppose I have a very small computer. They're 9-bit addresses. So they're 9 bits. And so I want to know if this is my memory word and it ends in 1101, where does it fit in cache? The simplest thing to do, suppose I have a 16-word cache, is just look at the last 4 bits and put it at cache location 1101. Right? That gives me a unique place to put every word in memory into cache. Just look at the last 4 bits and put them there. So then, if your computer says, please read address, something, 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 1101, and that one happens to be in memory, it happens to match the data you put there, that's called a cache hit. It gets it, it's fast, that's the good case. If it's not there, if you've stored a different word in that cache location, because the leading 5 bits don't match, because lots and lots of different words all get mapped to the same place, that's called a miss. It's not the data you want. In that case, it has to go to the slow memory and go get that and throw away the guy you had there before. Right? So it has to make some space because both guys want to get mapped to the same location. They'll throw away the old one, bring in the new one. So it doesn't always have to do that, but that's the simplest model. The other thing it can do, as I said, is take advantage of the fact that you don't want to just get one word usually. Usually you want a sequence. So if you access, so for example, you want to do a load of that location or that location, it'll always get them both because they're side by side in memory. They're just one address apart. And and they only differ in the bottom bit. If you do a read of either one, it'll bring them both in for you because it costs no more to bring them both in than to bring in one. So that takes advantage of spatial locality. And finally, some of these caches have what's called associativity. That means that unlike this case up here where everybody who ended in 1101 had to share the same location, so you could only have one, you could have the hardware built so that you could have 2 or 3. You could have up to 16 different values that all end in 1101 stored at the same location. That's called associativity. And that's more expensive. Not everybody builds their hardware that way. Every manufacturer makes different decisions, but this is part of the design space of how caches look, and it affects how fast your programs run. So please ask questions. So as I said, this is a deep dive for 1.5 lectures on how the hardware works, just to give you some appreciation of the complexity of performance and how to, at a high level, think about your programs so that you have an abstraction of this, because our goal is to have an abstraction, not worry about all these levels of detail so you know how to write your programs. Okay, so why do we have multiple levels of cache? So it's because if you only had one level and you insisted it fit on the chip, it couldn't get very big. There's a limited size to the chip, so you want to have larger caches off the chip. And not every manufacturer makes the same decision. So for example, Cray, who's also built the supercomputer Hopper that you're going to be using for the homework, one of their older supercomputers had too many levels of cache, and so they decided to throw one away between one manufacturing run and another. And IBM has another funny level of cache called a victim cache. And there, what they do is that, remember I said that if you try to read a word from memory and you have to throw somebody else out because they all would want to be stored at the same location, what do you do with the guy you throw away? You call that guy a victim. You may have wanted to access him again, and so they have a little special extra cache that grabs the victims, the last few victims, so just in case there was a mistake for them to throw it out, it's still there. So this is just the way they build their hardware, and so there is no one perfect way to do it. And let me say that there's lots of other levels in the memory hierarchy that work the same way. I talked about registers and caches in DRAM, but there are also pages, because if your program is too big to fit in DRAM, you still want your computer to run it, and it goes off to disk, right? The hardware will automatically move data in and out of your DRAM onto disk when necessary so you can run your really enormous program. And it uses something called a TLB, a translation look-aside buffer. So, a three-letter acronym, we'll leave it that way. So it remembers which pages of your memory are stored in disk and which pages are stored in DRAM. And so it has to look that up too. And so just to make it easier to program, right? You can pretend your computer has an infinite memory because of this. If it fits in disk, it'll run. Okay, so what I want to do now is take all that complexity and measure it and see what impact it has on the behavior of an incredibly simple program. This is what's called a micro benchmark because it's really small. So all I'm going to do is take an array of data that's stored in memory, so each of these is a word in memory, and I'm going to time the following loop. And in fact, because this is usual in science, you want it repeatable, I'm going to time this many, many times and take the average because there's some variation in the timing. And all I'm going to do is loop from the beginning of the array to the end. It's of length L, so loop from 0 to L and load A0, load A1, load A2. The simplest thing you could imagine doing. I'm going to time that, okay? See how long it takes. And it's going to depend on L, so it's actually a bunch of different experiments. But I'm also going to do a slightly different experiment. I'm going to vary it slightly. I'm not going to just take every consecutive word of memory. I'm going to take every second word of memory and time that. I'll take every fourth word of memory and time that, every eighth, and so forth. And the distance between consecutive words that I read and try to measure, I'm going to call that the stride, S. So my experiments are going to be, I'm going to do a bunch of different lengths. I'm going to pick a bunch of different strides, going from 1 word to 2 words to 4 words. And I'm just going to, and then I'm going to time it many times and take the average. And so the question is, what do you think we're going to get? Okay, so let me just, so when you do an experiment, you should have a mental model of what to expect so it makes sense, right? So you can sort of do, say, did I collect the data that makes sense? So here's how I'm going to plot the answers. I'm going to have a graph here. The horizontal axis is going to be the stride. The vertical axis is going to be the time per access, right? So the total time to run it divided by the length, L. And then for each, what I'm going to do is collect all the data for one array length and connect them together as a curve on this plot. So I'll pick like 32K length vectors. I'll access it for stride 1, stride 2, stride 4, and I'll get a curve that moves along here. And I want to see how that performance behaves. And so, so that's what I'm going to do. So let's just sort of ask ourselves what to expect. So because these machines are going to access not just grab one word at a time, they're going to grab multiple words at a time. So that's called the cache line size, right? They might not grab just one word, they might grab 4 when you grab one of them. So suppose that you are accessing every word in memory, but whenever it goes to memory, it grabs 4. That means that you can use all those 4, it's going to run really fast. But suppose your stride is 2, and you've gone and grabbed 4 words of memory. How many of those can you use? You're going to skip every other one, so it's grabbed a bunch of words you don't need. It's only going to run maybe half as fast. Right? So these are the kind of things that we expect. So one thing we expect is that if everything is so small that it fits inside the L1 cache size, that once you've run the algorithm once, it's all sitting there, and it should run just at peak speed, right? It should run at the speed of hitting the cache hit. Right? It's a cache hit time, right? So if the array length is very small, it doesn't matter what the stride is, it should just fit, and you can just read off the plot how big it is. Now, I'm going to do that for, arrays of successively longer lengths, and eventually the total size won't fit anymore. So it should take longer. So here's what I claim it's going to look like once we fall out of cache, once it no longer fits in cache. So it's going to take longer, longer, longer. It's going to take some fixed time, and then it's going to fall off again. So this is what we should kind of mentally expect to look at the data, which is on the next slide. So why do you think it looks like this? So what do you think the top line is? That's going to be the memory time. So that's going to be the time it takes to, if you're just getting one word out of memory, that's going to be the memory latency. Okay. So why does it not jump up there immediately if the size of your array does not fit in the L1 cache? Again, it's because when you go to memory and you grab 4 words at a time and you use every one of them, it's like you're getting a benefit from the fact that I grab 4 words, I use all of them. But if I have my stride is 2, I grab 4 words and I use half of them. So eventually you get to a point where you don't get any more benefit from having fetched 4 words at a time. Okay, and then you just, every time you go to get a word, it's at the memory speed. Okay? So you can see that from this plot, we ought to be able to read off the cache hit time, maybe the size of a cache line, the memory time, all this stuff we can sort of backfit out of the data. So let me show you some real data. And so this is an old machine, and it's almost legible. Sorry about the yellow. So it starts with it goes from a 4 kilobyte to 8 kilobyte, 16, and so forth, all the way up to, I believe, 64 megabytes, so a pretty large array. So each of these lines represents is colored the same as this. So they all lie together. So for example, 4 kilobytes is all down here. 8 kilobytes is all down here. 16 kilobytes, not give it away, is all down there. That's the blue one. And then it jumps up. So what conclusions can we draw? That the L1 cache is 16 kilobytes on this machine. Because when I went from 16 to 32, it took a lot longer. Okay? And on this machine, that's exactly 2 cycles. So it takes 2 cycles to get to the L1 cache. So then we keep running things. Well, so before I go on to this, let me say what the 2 major takeaways is. The first takeaway is this is a mess. This is complicated, right? But this is how computer hardware actually works, right? And so what you'd really like to do is write your program so that with high probability, it only takes you 6 nanoseconds to access memory and not 400 nanoseconds to access memory, right? You'd like to do something sensible so that you're living down here and not up there and not have to worry about all this complexity because there's a factor of 66 difference from the top to the bottom. And it depends in this complicated way on both how long your array is and on the stride. So now what I'm going to do is go back and try to tease out all the hardware parameters, reverse engineer what this machine actually looks like. And there's a question. Why does it come down at the end? So that's, okay. So the question is, why does the plot come down at the end? And so let me give you a hint. So if my array is of a certain length, L, and my stride is S, how many words am I actually executing? How many words am I actually accessing? L divided by S, right? So what if L divided by S, what if S gets so big that L divided by S fits in cache? So here, this is sort of this effect that I'm really accessing a much shorter array in effect because maybe it's 1 million words long, but if I'm only accessing every 500,000th word, I'm really only accessing a few words, right? So, and then it all fits again, so it drops down. So the interesting stuff is happening on the left of the graph, and on the right, it's just because things are effectively getting shorter. Was that your question too? Yes. Right, so there's all sorts of interesting issues that you can tease out of this. So the first one was the size of the L1 cache. So there's the next one, and I would claim that's the size of the L2 cache. Right? There's another bunch of horizontal lines, and they all land in about the same place as I go from 32 kilobytes to 64 kilobytes up to 2 megabytes, but when I go to 4 megabytes, it starts going up. And so I can draw the conclusion that I have a second layer of cache, and it's 2 megabytes in size, and I can look and see how fast it is, and it's 12 cycles. All right, so a factor of 6. And then, finally, that's the main memory, and that's, I don't know how big it is, but everything fits in main memory here, and that's running at 132 cycles. And so that is the slowest level of the machine. So, but the other thing we can ask about this is there are these corners, right? There's a corner, there's a corner, there's a corner. Where do these corners come from? So I claim that I can read off from that corner the line size of the L1 cache. So here's the claim. The claim is that when you read a location from memory and it brings it into cache, into L1 cache, it doesn't just get you one word or one byte, it gets you 16 bytes. And I can read that off from that particular fact where this line goes up and then it flattens out. And here's why. Here's how long it takes to read something that doesn't fit in L1, but I'm using every word. And that's when the stride is 4 bytes equals one word on this machine. So here I'm going to 8 bytes. It runs more slowly. It's because I'm only accessing every other word of the whole line that I read in. Here, I get to 16 bytes, and there it flattens out. So at this point, I'm only using one word of every cache line that I've read into memory, and that's why that corner is there. And so you can determine that. You can do the same analysis and decide that that corner tells you that your L2 cache line size is 64 bytes. And if you really want to figure this out, it turns out that there's a translation look-aside buffer. This is the hardware that figures out whether your page is stored in disk or in main memory. And you can figure out that your machine has 8K pages and 32 entries in your translation look-aside buffer. So if you want to do a lot of details of computer architecture, you can reverse engineer the entire machine from this picture. And we don't want to do that, beyond this lecture, but I'm just telling you that there's this enormous variation in an incredibly simple program and how fast it runs. Okay, so are there any questions about this before I come up a little later? Yes?
This might be more depth than what you want to do, but I see why it's 8K pages, but what's the intuition for a number of TLB entries?
So the length of the array, let me remind myself of the math there. So I think what we did was we said the leap here, this worked up to 256, and then up here it went to 512. And so if I have 256 length array, and they're 8 kilobyte pages, that means, and I divide those two, then I have 32 entries in the translation look-aside buffer. So yes, so you have to, so each of these comes from doing a little division about sizes, and we can talk about it later, but I don't want to do more in this course other than impress upon you this is the way performance actually works. Okay, so let me just give you some eye candy about some other machines. I chose this one. This is a very old machine. This is a 333 megahertz machine. I don't know, it's a decade old, because we can understand everything because it was a very simple machine. Modern machines aren't quite so simple. Here's another one which is on an older NERSC machine. And people try, and it looks rather different from before, and people tried in the same technical report to tease out the different sizes. I'm not going to try to do that here. And here's another one just to show you it's completely different again. And the reason I put this up is because it reminds me of a recent Parlab retreat where all the faculty and all the students and all our Intel collaborators all gathered together every 6 months. And a student had been doing benchmarking on a new Intel processor and put up a plot like this in one of the posters and was trying to explain it. By the end of the evening, there were 5 Intel engineers arguing with one another about why it looked like that. Right? They all had their laptops out and their spreadsheets and their NDAs, and they couldn't agree. Right? So even if those folks can't agree on why it looks like this, it's complicated, right? But this is what we have to live with. Okay, so there's one other feature of these modern machines that I want to illustrate with a benchmark. And that feature is called prefetching. The fact that they try to make a mathematical model of what your instruction stream is, of what addresses you're accessing, and guess and get it before you want it. So it's there when you need it. And so what I want to show you is a slightly more complicated benchmark. It's not very different, that tries to measure that. And this is called the stanza triad. And the only difference really between this benchmark and the last one is instead of having a fixed stride, what it does is it goes and reads L consecutive words, and then it skips K, and then it reads L consecutive words, and it skips K. And so where would this come up? So imagine you have a matrix, and it's stored column-wise, and you want to take a part of one column and a part of another column and add them to one another and add it to a third column. This is a kind of a typical thing in Gaussian elimination. So here's the kind of thing you might do. So this is a multiple of one column, and you add it to another column, and you get this one. So all those so here are consecutive entries of a column, because if it's a column-oriented matrix. But if you don't do the whole column, you skip a bunch and you go to the next column. So this is sort of a typical access pattern. And so what I want to do is understand how fast does this machine run, so, as a function of L and K. We know that if K were 0, if it skipped nothing, that's the simplest case. It should run at the peak speed that I had in the previous slide. And so the question is, when I do this skipping, how good is the hardware at recognizing that and getting you what you want anyway? And so here's some experiments that show that. There are 4 different machines, a Pentium 3, an IBM G5, an Opteron, and an Itanium. And for each machine, I do 2 experiments. The solid line is just the peak speed of reading stuff from consecutive memory locations, so no skipping, so that's a horizontal line. And then the other experiment is where I do some skipping. And here's how much I skip. I read a bunch and I skip 16. Excuse me. I read 16, I skip a little bit. I read 32, I skip a little bit. And the question is, how good is it at recognizing the pattern? And so for the Pentium, it's just fine. Independent of the length and the skipping, it always runs at the peak speed. So it did a pretty good job. But for these other ones, you notice that when the length is pretty short, the prefetching mechanism does not do a very good job of recognizing the pattern, so it runs. The vertical axis is performance, so up is good. And this green dot is much below that peak speed machine, so it's not doing a very good job of recognizing the pattern if you're only doing 16 words in a row. But by the time you're grabbing 512 words in a row and then skipping something, it gets the pattern down perfectly well, and you get near to the peak bandwidth of the machine. And all of these guys have the same property that when you only read a little bit and then skip, it doesn't recognize the pattern. But by the time you read enough, it gets the pattern down, and it gets you most of the peak speed of the machine. So prefetching is complicated. So let me now finish this part of the talk, this incredibly deep dive into what the hardware looks like, and say the obvious thing, which is that the actual performance of a very simple program can be a very complicated function of the architecture. You change the architecture slightly, the performance, you change the size of your loop, and the performance can change significantly. We had factors of 66. And so if you're going to write fast programs, you can't ignore this. I mean, somehow you have to capture that, or hopefully, abstract it away, but you have to deal with it. Because you don't want to ignore factors of 66. So what we want is a simple model of all of this complexity that helps us recognize how to write fast programs, which is what I'll spend my time on now. And so the technique that I'm going to use is called blocking or tiling. And basically, it's an idea of divide and conquer, which is a really common algorithmic technique that will automatically try to make sure that your program has a lot of locality. That when you access a data structure, you're always going to access stuff that's nearby, and you're not going to be jumping around in memory very much. And we're going to use matrix multiplication as the example of this blocking or tiling technique, but it applies to many other algorithms as well. So are there any other questions about that very deep dive before I sort of go up a level of abstraction? Well, I'll tell you about one more bit of hardware detail, but then I'll jump up a level of abstraction. Okay, I want to tell you about parallelism inside single processors, because that's something else you have to worry about. And this is mostly hidden from the software. Good compilers can take advantage of it, but again, they don't always do that. And the thing that I'm going to tell you about is pipelining and SIMD units. Single instruction, multiple data. I'll explain what that means. So I talked about pipelining before, and I mentioned a factory assembly line or the highway from Berkeley to Sacramento. And here's another one that you may appreciate, a laundromat. So suppose there are 4 people that go into a laundromat, and there's 1 washer, 1 dryer, and then you got to fold. How long does it take people to actually do the job? Suppose the washer takes 30 minutes, and the dryer takes 40 minutes, and the folding takes 20 minutes. If there were only 1 person, that would be a 90-minute job, okay? But it's pretty obvious that if you walk into a laundromat, you're not going to wait till 1 person is finished and then get the next person started. As soon as the washer is done, the next person B is going to put in their load in the washer. And as soon as that is done and the dryer is done, then you can just keep loading things up. And so here's a timeline of who is doing what. And so I want a simple mathematical model to capture this property and apply it to hardware. So in this case, if I insisted that only 1 person were allowed inside the laundromat at a time, and there were 4 people, A, B, C, D, each one took 90 minutes, it would take 6 hours to do the whole thing. If I do it pipelined in this pattern and I sort of maximally overlap the simultaneity of folding and washing, and drying and washing, then the pipelined execution takes, well, there's a 30-minute startup time, Then there's this pipeline of 4 stages of length 40, because the dryer is the bottleneck. And then there's some folding at the end for 20 minutes. That takes 3.5 hours. So the term we're going to use to capture this is bandwidth, which I've used before. And that's measured in loads per hour, or bits per second in the case of a computer, or cars per second in the case of the highway. And so if I don't do any pipelining, then I can do 4 loads in 6 hours, so 2/3 of a load an hour. If I do it with this pipeline fashion, I do 4 loads in 3.5 hours. That's a much higher bandwidth. But what's the limit? What's the upper bound on how fast this laundromat can work? It's if I had 1,000 people standing in line for this laundromat, it'd be pretty messy, but it's basically the dryer, right? Everything matters in the dryer. And if you end up with basically 1.5 loads per hour that you can do in the long run. And that is the bandwidth of this particular pipeline. So pipelining helps the bandwidth, but it doesn't help the latency. I mean, when you walk in, it's still going to be 90 minutes before you're done with your laundry, right? So this is why bandwidth and latency are 2 different quantities. They're both important, but they're different. And the bandwidth is going to be limited, in this case, by the dryer, the slowest stage, right? So when you build your pipelines in hardware or in a laundromat, you'd like every stage to take about the same time. The longest guy is the bottleneck. And what's the potential speed up? Well, here it's really just a factor of 3, because you can do at most 3 things at the same time: fold, dry, and wash. And so the number of pipe stages is your speed up. And so this is a laundromat, but all hardware, including sequential hardware, is built this way. So here's a picture of a data path on a sequential processor called MIPS. You can look in Patterson and Hennessy's textbook for details. So how does a computer execute a single instruction? It breaks it up into a pipeline, just like I had before, and there are typically 5 stages. So the first thing it has to do is it has to go get the instruction. It has to know, what are you telling me to do next, you programmer? So it goes and gets the instruction. The next stage of the pipeline is it has to look at that instruction, take it apart, and decide, are you asking me to do an add? Are you asking me to do a multiply or a load or a store? That's the next stage. The next stage is to actually execute it, right? Do whatever you told me to do. The next stage is, if you told me to go to memory, I have to go send an instruction to the memory to go read or store. And then finally, I have to write back the answer into the cache. This is a 5-stage pipeline. All of them can go at the same time. And so in principle, the hardware can go 5 times faster for many instruction streams, unless something goes wrong. And if one instruction depends on the next instruction, you can't do them at the same time, right? You got to wait. But if your instructions are independent of one another, you can do 5 at the same time. And so even inside these units, this is the arithmetic logic unit. That's where the adders and the multipliers are. You have the same pipelining deep inside there. So if you want to multiply 2 floating point numbers, you have to take them apart. You have to take out the exponent and the fraction, do different works on the exponent and the fraction. It may take 10 stages in your pipeline to multiply 2 numbers. That's all hidden inside there, again, to make it go faster. So you might be able to have 10 floating point multiplies sort of in flight at the same time. So that's pipelining. The other kind of automatic parallel hardware that's built in is called SIMD, or single instruction multiple data. So in this case, a typical scalar machine with no parallelism would say, take X in a register, take Y in a register, put the sum in a register. What SIMD machines do, and this is like in all Intel platforms, their special name for it is SSE or SSE2. If you happen to have 4 words side by side and another 4 words side by side, and you want to compute the sums of each pair, a single instruction will do that for you and do it in parallel. So for this to work, things have to be, these can't be in random locations in memory. They really do have to be side by side for the hardware to be able to do this all in one instruction. So here's what it looks like. If you have 4 words and they're all side by side, it'll do all 4 of them at the same time, 4 single precision floating point operations. But what about double precision, right? This is like 64-bit numbers. Those are 32-bit numbers. The limit is, as long as you can fit them side by side into a total of 16 bytes, it'll do them in parallel. So it'll do 2 double precision floating point operations in parallel for you. And what if you're just doing sort of byte operations, like you're doing ORs or comparisons of really, really short numbers? You can fit 16 of those in there, and it'll do 16 things at the same time. So whatever fits into 16 bytes, it will do in parallel for you. So now the trick is, this all has to be lined up in memory. They all have to be contiguous. the address of this first guy can't be arbitrary. He has to be at the beginning of a cache line. He can't be in the middle of a cache line. So that gives some constraints on how you set up your data structures. And if you're programming on GPUs, the same story happens. Everything has to be lined up. But I'm just explaining, and we'll have a lecture on GPUs later. I'm just giving you this simple example on SSE. So what does this mean to you? It means that sometimes you have to think about how you organize the inner loops of your program so that the compiler can hopefully take advantage of these things. And in fact, some of these machines have special instructions to pay attention to. Again, they put them in because people do it so often. So here's an instruction on a lot of platforms. It has 3 arguments, C, Y, and Z, and it does a multiply and add, and it gives you one result. That's called a fused multiply add. So why did they build in this special instruction to a lot of computers? It's because a lot of people do linear algebra, for example, and this or signal processing. This is like in everybody's inner loop, right? You're multiplying 2 things and adding it. And so they said, let's make a special instruction just for that. And so hopefully your compiler will recognize it. And so it will just do a good job and generate that kind of code for you. But in practice, it may not always do that. There are flags in the compiler, sort of optimization flags to try, that say, do it this way, do it that way. And you can rearrange your code to make it easier for the compiler to recognize this. And you could even write assembly language. That's sort of the worst case. And you will, on assignment 1, explore this for just one assignment and see what the impacts are. And then move, for the rest of the semester, as I said, we'll move up the hierarchy and not worry about these details. Yes, Phil, question?
I just want to throw out the room. The other reason
Oh, wait, hold it, hold it. We want the people in the overflow room to hear too.
I just want to throw out some additional factors. The other reason your compiler may not recognize this is, depending on your language you're writing in, it may actually change the semantics slightly, where you may get a slightly more precise answer than you would have gotten if you'd done the 2 independent operations.
That's right. So to be more specific, it might multiply those 2 numbers in double precision. So that intermediate term will be more accurate. And when you do the sum, the final answer will be more accurate. And so without even asking, the machine will give you a more accurate answer than you thought you would have gotten. So indeed. OK. So now that we're now finished with all of the deep dives into hardware. And I want to apply these ideas to optimizing matrix multiply, the most analyzed algorithm in the world. So I'm going to use these performance models to try to understand its performance. I'm going to tell you about lower bounds on how much data has to move no matter how you write matrix multiply. As long as you do the usual n-cubed operations, how many words do you have to move between fast and slow memory? And I'll show you an algorithm that attains it. And to get warmed up, to make sure we understand the model, I'm going to do something a little simpler, which is matrix vector multiply. And then I'll go on to matrix. And I won't finish today. I'll continue it next time. So why matrix multiply? It's an important kernel in many problems. And so, for example, if you ask, how do you actually do Gaussian elimination or find eigenvalues? If you look inside the inner loops, it's doing matrix multiplies, because people try to reduce it to that. And of course, if you want to rank your computer as one of the top 500 in the world, you're going to spend all your time doing matrix multiply. So there it is. It's one of those 7 dwarfs, or 13 motifs. I'll remind you of that in the picture on the next slide. And actually, it's related to a lot of other algorithms. So basically, all of linear algebra is 3 nested loops. I'll remind you what they are, but you can imagine the usual 3 nested loops you write to do matrix multiplication. That comes up not just in linear algebra, but in some areas like graph theory, like all pairs shortest path in Floyd-Warshall. So what we learn about how to optimize for matrix multiply does apply to other areas. As I said, this is a very well understood algorithm. And just to remind you of our picture about the 7 dwarfs, or the 13 motifs, this is the dense matrix operation. And wherever you see a bright red box, that's where it is heavily used. So it comes up not just in high-performance computing, it comes up in machine learning and games and all these other applications too. So for motivation, let me show you a plot of the naive algorithm, 3 nested loops, versus an optimized algorithm on a very old machine, just to give you a hint. So the horizontal axis is the dimension. I'm multiplying 2 square matrices up to dimension 800 by 800. Vertical axis is performance, so up is good. The peak, this is a very old machine, is 330 megaflops, so it's just a little bit off the top of the screen. Here's your favorite 3 nested loops. With the compiler to have all the optimizations turned on, it's running at about 10, whatever that is, 20 megaflops. And here are 2 optimized versions. One of them is provided, the red line is the hand-optimized code provided by the vendor, where they have a team of people at Sun, now Oracle, who spend their lives tuning stuff like this. And the blue line is an automatically built, an auto-tune version, where we wrote a program that searched over all possible reasonable ways of doing matrix multiply and automatically found the best implementation. And that's the blue line, which is about as good. So you can see that there's a big gap there, and we'd like to either find the optimized library from the vendor and use that, or if that doesn't exist, because it certainly doesn't exist for every application you'd want, we'd like to be able to build an auto-tuner that would find it for you automatically. And then, of course, you might just have to do it by hand yourself. So let me give you a little more background. So let me just tell you a little story here. This auto-tuner is called FEPAC. And this was the one I think I told you about last time, where from homework 1, nobody had ever beaten the hand-tuned code from the vendor before in the race that you'll all do at the end of homework 1. Except 1 year, quite a while ago now, 2 teams actually beat the hand-tuned code from the vendor. And the teaching assistants were so surprised that they took they looked at the students' code, they said, what did these people do? And they built this little search engine to try all the different possible implementations, and it turned into this into this project. So FEPAC was the original one. The best auto-tuner now is called Atlas, excuse me, Atlas, and ATLAS. And I think there's a link on the website. So people still use this, not just for matrix multiply auto-tuning, but they do it for many things. So let me talk about matrix storage, because I have to sort of talk about data structures here. So a matrix, we all think of it as a 2-dimensional array of elements, but of course memory is 1-dimensional, right? Successive addresses are stored in successive locations. So we have to have some convention for mapping our naturally 2-dimensional object to 1 dimensions. There are actually a lot of ways to do it, but the 2 simplest ones that I'll start with are column major and row major. And if you're used to programming in a language like Fortran, column major is the natural one. So columns are stored in consecutive memory locations, so address 0, 1, 2, 3, 4, 5. And if you're used to programming in C, it's row major. And so they're stored that way, and they're close enough. Your intuition is good enough for either one. So what does this look like when it's actually stored in memory? So here's my 2-dimensional matrix. And here what I've drawn are cache lines. So where is it stored in memory? So here are, let's say, 4 consecutive words that's stored in one cache line. And that's the first part of the top of the first column. And then the next 4 words that column are stored in another cache line, and so forth. And then I go on to the next column and so forth. So if I want to access that matrix by a column, this is great. Because what do? I bring in one cache line, I get the next 3 entries. I bring in that word, I get the next 3 entries. That is optimal for the accessing that matrix. But I don't need to just read down columns. If you think about matrix multiply, I need to take the dot product of a row and a column, right? That's what it looks like. So I also have to access this matrix row-wise. So here's an example of a row. And let's just think about what that means. When I ask for that entry of the matrix and read it from memory, I not only get it, I get everything else in that red cache line. So I'm not going to use them, though. Then I go get the next entry. I get all those cache line entries. Then I get that one. Then I get that one. And so what I've read into memory is everything that's colored red. What I've read into cache is everything that's colored red. And that may or may not be a very useful thing the next time around. And so we are going to have different data structures that get around this problem. But in the meantime, this is what it looks like. So let me give you a very simple model that's going to tell us how to do the optimization. How are we doing on time? OK. I'm going to assume there are just 2 levels of memory, so fast and slow. And if you have more levels, then we will just apply this idea hierarchically. But just to think about it, we have fast and slow memory. And initially, all the data is in slow memory. And I have to bring it from slow to fast to do the work. So here's going to be my very simple model I'm going to use to say, am I doing as well as possible? I'm going to count M, which is the number of memory elements or words that are moved between fast and slow memory. That's going to be the bottleneck. I'm going to have a hard, so that depends on the algorithm. Then I'm going to have the time per slow memory operation. That's a big number, right? That's a hardware parameter. Then I'm going to count the amount of arithmetic that I do, the number of floating point operations. And I'm also going to have another hardware, and that depends on my algorithm. And then I'm going to have the time per arithmetic operation, another hardware parameter, which is a lot less time than getting to memory. And then I'm going to use one other quotient here to sort of measure how good my algorithm is. I'm going to take the average number of flops per slow memory access. So divide the total number of flops by the total number of memory accesses. That number is going to come up in my performance model. So what's the minimum possible time? If memory were free, which it isn't, I would do flops times the time per flop. And if all the data were in fast memory, that's what it would cost me. So that's a guaranteed lower bound. I want to know how close I get to it. So what's the actual time in my very simple model? It's the flop time plus the memory time. Flops times time per flop plus memory accesses times time per memory access. And let me just do a little bit of algebra, and factor out the lower bound. So I'm going to write the actual time as a product of the lower bound times something that's bigger than 1. And I want to understand these two factors in there that make it bigger than 1. So this factor is the quotient of time per memory reference divided by time per flop. It only depends on the hardware. So this is a big number, but it's only dependent on your hardware. And this number here, the reciprocal of Q, that only depends on your algorithm. So I've separated out the behavior on the hardware and the behavior in the algorithm. And so this is a big number, right? If it takes me 100 times as long to go to memory as it does to do arithmetic, that number is 100. So what do I need to do to go fast? I need to have a very big Q too. So I take this big number and I divide it by something huge. I have to do a lot of floating point operations per memory access. It means I have to have good locality. So the larger the Q gets, the faster I can get to the minimum. But even if I only want to get within a factor of 2, right? So suppose I want to get within a factor of 2, Q has to be at least as big as Tm over Tf. So that gives me a property of my algorithm that depends on the hardware parameters. It has to be satisfied in order to get even within a factor of 2 of peak speed. So we have some names for these things. That ratio there, average flops per slow memory access, that's called the computational intensity. That's a property of your algorithm. And this other quantity is called the machine balance. So how many flops per memory access can I do? OK, so let me use that model to analyze a much simpler algorithm, which is matrix vector multiply. So here are my, now just 2 nested loops instead of 1 nested loop. I'm going to take the matrix A, multiply it by x, and add it to the vector y. And what I've color-coded in here is what is the inner loop doing? It's taking a dot product of the ith row of A and the column vector x, and it's sticking it into the entry y. So what I'm going to do now is, so that's the simplest code. I'm going to annotate it by saying when does a memory motion actually occur, right? Because when you write code, you don't say move, when the memory traffic occurs. That's what we have to reason about. So I'm going to put in some comments to say when the memory actually moves. So I'm going to assume that I can read the whole vector x into fast memory and just keep it there. So I'm going to assume that that fits in cache. Then I'll read the whole vector y into fast memory and keep it there. And now I actually go into the program. And inside the loop, I need to compute the dot product of the ith row of A with x. So I have to read in the ith row of A into fast memory. Then I do my dot product. There's no memory traffic inside the dot product that runs at peak speed. And then when I'm done, I just put the answer back into memory. So that's sort of like the obvious way you can do it. And you can't go any faster than this. I'll just appeal to your intuition. But let's count, see how we've done. What are the number of slow memory references? Well, I've read x, that's n. I've read y, that's another n. I've written y, that's another n. So 3n altogether. But the big guy is A. I've read every entry of A exactly once, so that's n squared, since it was an n by n matrix. What's the number of memory of arithmetic operations? Well, it's n times 2, because I have 2 nested loops, and I'm doing 2 operations inside, and so I'm doing 2n squared. So what is the computational intensity? It's 2n squared divided by this, and when n is large, it's about 2. So 2 is a very small intensity, right? I'm doing 2 floating point operations for every piece of word of memory that I read in from A, and so I am doomed to go at the speed of slow memory. This is necessarily a slow algorithm. I can't go faster than slow memory speed. So let me use this model and compare it to some benchmarks to see if it tells us something useful. And so what I'm going to do is compute the time for doing 1,000 by 1,000 matrix vector multiplication. And I'm going to use this formula from before. I'm going to count the number of flops, which is 1,000,000, times 2. I'm going to measure for a whole bunch of different machines. So these are UltraSparks and Pentiums and Powers and Itaniums, so lots and lots of different machines. And I'm going to use some benchmarks to compute the time per flop and the time per memory access. And I'm going to use this incredibly simple formula to estimate how long matrix vector multiply takes. So remember that the machine balance, this is how many flops I can do in the time of one memory access. Here are the numbers from these benchmarks. They're all, at least 5. And sometimes they're 24. You can do 24 flops in the time of one memory access. But matrix vector multiply only does 2 flops per memory access. So this is why we can't possibly go very fast. So let me see what the values are. Well, let me just say I did have some simplifying assumptions here in the model. I've ignored parallelism, right? Because maybe you could overlap memory traffic in the arithmetic. That would give me a factor of 2 maybe, but it's still not going to do that much. I assumed the main memory was fast enough to hold all of x, all of y, and a whole row of a. That's not a bad assumption. This matrix is small enough. It's only 1,000 words, so that fits all right. But if your matrix were really, really big, I couldn't assume that. And I'm also assuming that going to cache doesn't cost very much. That's an okay thing too. So now, given all those caveats, let me show you the data. And so here are all these different machines. So every triple pair of bars is a different machine. The vertical axis is megaflop, it's performance, so up is good. The red and the blue are 2 versions of the performance model. They get the same answer, so it didn't change very much. And the green is the actual performance on all these different machines. And so you can see, this is considered a good approximation in this realm of computer science. It does a pretty good job, within a factor of 2 or maybe even 25% of approximating what the runtime is. And so our model, that it's all the time spent in memory, does do a good approximation on all these different platforms. So let me just say that the difference between the 2 models is, do you count the time to move x and move y or not? It didn't really matter. That was a low-order term. Okay, so now we tentatively believe our model, that all I have to do is count the flops, count the slow memory accesses, and add them together. So let's apply that to matrix multiply, see what happens. So here is naive matrix multiply, 3 nested loops, I, j, k, all going from 1 to n, and the inner loop is doing what you think, and here's a picture of it. The inner loop is taking the ith row of A, the jth column of B, doing a dot product, and putting the answer in the ijth entry of C. So that's a perfectly reasonable way to do it. So now, how many floating point operations does this algorithm do? It's doing n times n times n times 2, so it's doing 2n cubed. And how much data is it inherently working on? Well, I have n squared plus n squared plus n squared, so it's only 3n squared worth of memory, and so my computational intensity is potentially as big as n. That's enormous, right? It's 1,000 or 1,000,000. So I have a good chance now for this algorithm, unlike matrix vector multiply, of actually going as fast as the hardware can possibly go. But not with this algorithm, right? Not with this implementation. So let's see how well we can do. And again, what I'm going to do is annotate it by saying when the data actually moves, because looking at the source code, it's not there, but we can reason about it. So here's sort of the least data movement you could get away with. So when I come into here, in the I loop, I'm going to read this whole row of matrix A into fast memory and keep it there, because I'm going to use it over and over again. So I just want to read it once. Then into the J loop, I have to come in, and I need to read that entry of C, so just read that one entry. And then I have to read that column of B, so I can compute the dot product. Then the inner loop computes the dot product, and I write the answer C back to slow memory. So that's sort of the, intuitively, and in actuality, the least you can do with that particular algorithm. So let me now count how much memory traffic I actually did. So I read row A, row I of A into fast memory, and I do that for I equals 1, 2, 3, up to n. So basically, I've read every row of A once. So what's the total number of reads of A? N squared, right? I've read the matrix A exactly once. Can't do any better than that. So how about C? There I read Cij, and then I write Cij. So how many reads and writes are there of C? N squared reads, N squared writes. Can't do any better than that. So that sort of hits the lower bound. All right, what about B? How many times do I read B? So let me just, so just this one line here, read column J of B. That's n words, right? And it's inside 2 nested loops. So it's n times n times n. N cubed reads, right? That's the bad news. So I'm actually doing as n cubed reads and n cubed flops. So here's, I'm just written it down again. So I'm doing n cubed to read each column of B n times. I just read A once. I read and write C1, so the total number of amount of memory traffic is n cubed to a first order. And so the actual computational intensity, flops divided by memory traffic, is 2n cubed divided by n cubed, which is 2. It's no better than matrix vector multiply. So even though I had this opportunity to do a lot better, I'm never going to go any faster than matrix vector multiply. And that's exactly what happens in this plot I showed you before. When you write the 3 nested loops and tell the compiler to do the best it can, it's running at the speed of matrix vector multiply. But we know we can go this fast. By the way, why do you think it looks like this and then suddenly drops? Yes?
You can fit the entire matrix into cache.
Right. The answer is you can fit the entire matrix into cache, and you can read up from where this cliff is how big the cache is, right? Because you 3n squared equals the cache size, and you can read off n, and so you can reverse engineer the hardware again. Okay. So actually, the naive algorithm is even worse. Let me just show you another experiment that somebody else had the patience to do. I didn't do it. So let's suppose you ran the naive matrix multiply on a very old machine, an IBM RS-6000. And here on the horizontal axis is the problem size on a log scale. And on the vertical axis is the performance on a log scale. Okay, so the inverse performance, the number of cycles per floating point operation. Right? So normally you'd expect to do 1 cycle per floating point operation. Well, I'm going to take the log of that. So that means 10 cycles to do a floating point operation, 100 cycles, 1,000 cycles, 10,000 cycles. This is sort of a measure of how bad things are because you're going to memory. So here is the red line is his data. And so for a little while, until he falls out of cache, or falls out of something, he's running at about 5 or 6 cycles per floating point operation. That's not too bad. Then there's a cliff. And then all of a sudden it's flat again. And here's another cliff. In fact, this was just a piddling little 2,000 by 2,000 matrix. It took him 5 days to run the naive algorithm to multiply a 2,000 by 2,000 matrix. This should be like milliseconds. And here, if he'd actually bothered to run the 12,000 by 12,000 matrix, it would have taken him 1,000 years. So he didn't do that experiment, but he did enough of it to kind of indicate what happened. So each of these cliffs represents falling off a different part of the memory hierarchy. So let me just do the diagnosis. So here, when we're down here, this thing, everything fits in cache, that's fine. That tiny little cliff is where you get a cache miss every 16 iterations. This cliff is where you get that TLB, translation look-aside buffer, miss every iteration. So it has to say, is this in disk or in memory? Is this in disk or in memory? It does that every time through. This cliff comes from actually getting a page miss every 512 iterations. So it has to go to disk to get your data. And here is where it gets a page miss every iteration. So every passage through the inner loop. And that would have taken 1,000 years. So that's just an estimate. So we want to do better than this, and we can. And so let me show you what that algorithm looks like. And it's called blocked or tiled matrix multiply. This is a general technique for many algorithms, and it's was first understood well for matrix multiply. So what I'm going to do is I'm going to think of my little n by little n matrices as containing not just entries but blocks. I'm going to break them up into little b by b blocks. So now that's not a 1 by 1 entry, that's a b by b block. And I'm going to have now capital N by capital N matrices where each entry is a b by b block. So b, the block size, is little n, the original dimension, divided by the number of blocks in each dimension. So that's how I'm going to organize the algorithm. I'm going to have 3 nested loops. And then what I'm going to do in the innermost loop is I'm going to grab that b by b block of A. I'm going to grab that b by b block of B, multiply them, and add them to that b by b block of C. It's exactly the same arithmetic operations that you did before, exactly the same multiplications, except I'm just adding them up in a different order. And so what I'm going to do is for every pair of b by b matrices from A and B, so A sub I k, B sub kj, I will multiply it. That multiply is a b by b matrix multiply, and I'll put the sum back into there. And so this program, even though I have 3 nested loops, this innermost loop here is actually another 3 nested loops, but I'm only multiplying 3 b by b matrices. So there are a total of 6 nested loops in this program. And so now let me count the memory traffic. And so what I'm going to do is once I know I and j, I'm just going to read that little b by b matrix C and bring that into cache and keep it there. Now I go into the inner loop with k. I will read that block of A. I will read that block of B everything, I'll assume it all fits in cache. I will do the multiply. So I'll do this little b by b multiply, assuming it all fits in cache. And then when I'm done, I'll just write that back out. So my assumption is that my little b by b blocks are small enough so that I can fit 3 of them into cache at the same time for this algorithm to only do that much memory traffic. So let me do the counting and see how well I do. So remember, m is the amount of memory traffic. My original matrices were little n by little n, and I broke them up into b by b blocks, and there are that many blocks then in every dimension. And so the memory traffic is going to be, turns out it's not going to be n cubed anymore, it's little n cubed anymore, it's going to be capital N times little n squared. So where does that come from? So each little b by b block of b, so if I look at this, I have 3 nested loops. So capital N times capital N times capital N times, please read that block of b. How big is that block? It's little b squared. So the total amount of memory traffic is capital N times capital N times capital N times little b squared. And so when I do that and it all cancels, it turns into capital N times little n squared. The same thing is true for A. I still only read and write each block of C once, so that's still the lower bound. So now my total memory traffic is no longer little n cubed, it's capital N times little n squared. And when I compute the computational intensity, it turns out not to be 2 anymore, it turns out to be b, it's the block size. So whenever I read b words in from slow memory to fast memory, I can do not just 2 words, two floating point operations, I can do b floating point operations. And I can pick b bigger and bigger and bigger, right? So I can make my computational intensity much, much larger. Question is, there must be a limit here. How big can I possibly make my computational intensity little b? There's some limit, right? I had some assumption to run this algorithm. What was my assumption about how big little b was? I had to be able to fit that block and that block and that block into fast memory at the same time. So that was my assumption. And so the assumption is that 3 times little b squared is less than or equal to the size of the fast memory. So m sub fast is the size of the fast memory. And if I do that, then my computational intensity equals b. And so if I want to build a machine to run matrix multiply at nearly peak machine speed, what I need to do is have it be big enough. I have to have the cache be big enough so that the square root of the cache size is at least about the time per memory operation divided by the time per flop, because that's what the formula said. And so I can look at all my different pieces of hardware here and say, what is the time per memory operation divided by the time per flop, this hardware parameter, and I can compare that to the size of the cache. And this says the cache has to be at least 14 kilobytes to run matrix multiply at full speed. Everybody builds caches that big. So matrix multiply should run at full speed. I'm almost done here. So this particular algorithm, let me just repeat what I said. It changes the order of operations. It's still doing the same n cubed multiplications. It's just adding them up in a different order. And that's legal because because addition is commutative and associative. You will not get the same answer as the old algorithm, right? Because of round-off errors. But most people are perfectly happy with that. But you should be forewarned. You'll get a different answer, but to within round-off, it's good. And so what we decided was that we were able to pick b as we want to pick it as large as possible, but we were limited by this particular limit, the square root of the cache size. Now, it turns out that there's a lower bound that says this is optimal. That no matter how you take that algorithm that does n cubed multiplications, no matter what order you do them in, no matter what cleverness you do of when you read and write from memory, you can't do better than this. And this is a famous theorem from 1981 from Hong and Kung, that any reorganization of this algorithm that only uses associativity and so it just reorders the additions, you can't do better than this computational intensity. And so in particular, it says that the number of words moved between slow and fast memory is big omega. That means it's lower bounded by some constant multiple of n cubed divided by the square root of the cache size. No matter how you organize it, I'm going to do n cubed flops, and this is how many words I'm going to move. N cubed divided by the cache size. And that is attained by this particular algorithm. The proof of this I'm not going to do today. I may or may not get to it during the semester, but this is a special case of a much more general result. So let me just repeat and try to summarize here. So this theorem that I just told you about is a lower bound on the amount of data communicated between slow memory and fast memory by matrix multiply. So it could be between cache and DRAM or between DRAM and disk. You can model it any way you like. So it tells you how much data has to move across any threshold in your memory hierarchy. So the other thing you might ask about, and this depends on your data structure, is that I'm not only interested in how many words I have to move, I'm interested in how many messages I have to send, right? Because I'm going to pack all those words into cache lines or something like that. What's the lower bound of the number of cache lines? And that can also be gotten from this theory. I won't do the details right now. But maybe the most interesting thing is that the idea behind this lower bound has been extended not just to matrix multiply, but anything that smells like three-nested loops. Right? There are a lot of algorithms in the world that smell like three-nested loops: Gaussian elimination, finding eigenvalues, least squares, graph algorithms. The proof works for all of it. And it isn't just true for dense linear algebra, multiplying dense matrices. It's true for sparse linear algebra. It's true for the sequential and parallel algorithms. This lower bound theory will tell us give us a criterion for an algorithm to be optimal. Will give us a lower bound on how much memory traffic there is. And even more recently, we've extended this lower bound basically to anything that looks like nested loops accessing arrays. We can write down a lower bound for any program that has loops and arrays in it. And that's recent enough that I hope it gets posted this weekend on the web page. So we're almost done with that paper. So needless to say, there are lots of class projects that are involved in order to implement some of these things. Are the lower bounds attainable? But there's lots of room now for big improvements in much of computation. And this is a good time to stop and let David and Michael tell you how to get accounts on the supercomputer.
All right, hi everyone. I'm Michael. I'm one of the GSIs. So before you use the resources at NERSC, they ask that you fill out a user agreement. For those of you who haven't read it, it's available online, or I have some hard copies up front. But basically, it just says you won't abuse the resources down there. So once you fill this out, you can give this form back to David or I, and we will submit it to NERSC. NERSC will actually call you and give you your password over the phone. So please be sure that you put down a phone number that you can be reached at. And they can't leave a message, so be sure to be near that phone over the next week or so. But they'll call you and give you a temporary password. You can change it online on the site nersc.gov, and this will allow you to connect to the supercomputers. If you have an existing NERSC account, just send David and I your first name, last name, and NERSC username, and we will just grant you access to our class repository. The way these allocations work is that they give us a certain number of hours, and we give each of you a subset of those hours, which should be enough to do the homeworks and your project. But if you want to use more hours on your project, email us later in the semester, and we can adjust your allocation appropriately.
So how many hours do we have for the class?
I'm not sure.
I think it's about 1 million, so it should work.
A million hours. Okay. Lots of time. Question?
So just to check, if we already have an account for like our research, we can, in the job submission script, for example, set that we want the hours deducted from the class repository versus the research.
Correct. Okay. So the question is, if you have two accounts, can you charge the class account for a particular job? The answer is yes. I think if you look at the QSub documentation page, there's a special flag, and you can pass the name of the account to Bill. Another question.
How the hour counted? I mean, as I log on, or is CPU hour?
You can log on and use
So can you repeat the question?
Oh, the question is, how are the hours counted? Is it the time spent logged on, or the CPU hours for running jobs? It only counts running jobs. You can log into the login nodes and compile code and edit code, but it only charges you once you submit it to the real machine.
Okay.
Any other questions? All right, so fill these out and give them back to David and I. Thanks.